Before we begin, pause for a moment. For decades, one technology was considered the absolute future of military aviation. It worked, it was spectacular, and yet, it almost completely disappeared. Stay until the end, because you'll understand why one of the most brilliant solutions ever created wasn't abandoned because it failed, but for something much deeper. Why did one of the most impressive technologies in military aviation almost completely disappear from modern aircraft? During the 1960s and 1970s, variable sweep wings represented the absolute future of aeronautical design. Aircraft like the F-14 Tomcat, the F-111, the Tornado, or the Soviet Tu-160 seemed straight out of science fiction. Wings capable of moving mid-flight, adapting to different speeds and missions. For many engineers of the time, this technology wasn't just an advantage, but the definitive solution to one of aviation's greatest dilemmas: how to combine slow, safe takeoff with efficient supersonic flight. If you're interested in this type of analysis where engineering, history, and military technology intersect, subscribing now is the best way to make sure you don't miss the next videos. The logic behind variable geometry wings was sound. At low speeds, extended wings provided greater lift, better maneuverability, and shorter takeoffs. At high speeds, by folding back, they reduced aerodynamic drag, allowing for more stable and faster supersonic flight. In theory, a single aircraft could behave like several different ones depending on the phase of flight. In the midst of the Cold War, this versatility was extremely appealing. Air forces needed aircraft capable of taking off from short runways, flying at low speeds during attack missions, and then escaping at supersonic speeds. Variable geometry wings promised to do it all. And pay attention, because in a few minutes you'll understand why this promise ended up becoming a problem that no one could ignore. The F-14 Tomcat is perhaps the most emblematic example. Its design allowed it to take off from aircraft carriers with its wings extended and then automatically retract them upon acceleration. For pilots, it was like flying a machine that transformed mid-air. The same was true for the F-111, designed as a long-range tactical bomber, and the European Panavia Tornado. During those years, many experts believed that variable geometry wings would become the standard in advanced aviation. In fact, several experimental projects explored even more complex configurations, with wings that changed not only their angle, but also their shape and effective surface area. If at this point you're already starting to see why this technology seemed unbeatable, leave a like. It helps this type of analysis reach more people. However, behind that technological promise lurked serious problems. The first was mechanical complexity. The wings of variable geometry required extremely robust hydraulic systems, reinforced pivot points, synchronization mechanisms, and internal structures much heavier than those of a fixed wing. All of this increased the aircraft's weight, reducing its payload and range. The second problem was maintenance. Every moving point was a potential point of failure. In harsh environments, sea salt, sand, extreme temperatures, moving wing systems required constant inspections, precise lubrication, and costly repairs. On aircraft carriers, for example, F-14 maintenance was notoriously complex and expensive. Furthermore, there was a critical structural problem. The point where the wing pivoted concentrated enormous stresses. At high speeds and during aggressive maneuvers, these loads could cause accelerated structural fatigue. Over time, this necessitated further reinforcement of the structure, adding weight and reducing efficiency. Stay until the end of the video, because here's the key. The abandonment of moving wings wasn't an isolated decision, but the result of a silent revolution that forever changed how aircraft are designed. Despite everything, for a time, technology continued to advance. Engineers were confident that the benefits outweighed the drawbacks. But while variable geometry wings dominated headlines and air shows, another, quieter revolution was happening in parallel. Advances in computational aerodynamics, composite materials, and controlled digital flight control began to change the landscape. New wing profiles, combined with fly-by-wire systems, allowed fixed-wing aircraft to achieve performance levels unimaginable decades earlier. The need to physically move the wings began to be questioned. The new generation of fighter jets demonstrated that it was possible to achieve excellent low-speed maneuverability and supersonic efficiency without resorting to complex moving mechanisms. The design of modified delta wings, advanced leading edges, and intelligent control surfaces began to replace the mechanical solution with an electronic and aerodynamic one. In parallel, costs began to weigh more heavily on military decisions. An aircraft with variable geometry wings was not only more expensive to build, but also significantly more expensive to operate for decades. In a context where air forces were seeking more sustainable fleets, that difference became critical. Let's pause here to invite you to like and subscribe to the channel if you're enjoying the video so far. The demise of variable geometry wings didn't happen overnight. It was the result of a profound transition in how engineers understood flight. Instead of adapting the aircraft to each phase through physical mechanisms, the new philosophy was to make the airwork for the aircraft using electronics, software, and advanced aerodynamic design. The first major shift came with the development of fly-by-wire technology. Fly-by-wire technology revolutionized aircraft design. Previously, airplanes relied on direct mechanical and hydraulic connections between the pilot and the control surfaces. This limited the design. A wing had to be inherently stable. With fly-by-wire, computers began interpreting the pilot's commands and correcting them in real time, thousands of times per second. This made it possible to design aerodynamically unstable, yet extremely maneuverable, wings. An aircraft no longer needed to change the shape of its wings to fly slowly or quickly. Electronic systems constantly adjusted flaps, elevons, canards, and rudders to maintain optimal control in any flight regime. The F-16 was one of the first fighters to demonstrate this philosophy. With a relatively simple fixed wing, it could maneuver at low speeds, sustain high angles of attack, and maintain stability at speeds approaching Mach 2, something that, decades earlier, had seemed impossible without movable wings. In parallel, computational aerodynamics revolutionized design. Engineers were no longer solely dependent on wind tunnels and physical testing. Computer simulations allowed for the optimization of wing profiles for multiple flight conditions, revealing much more efficient compromises than those available in the 1960s. This led to the development of wings with extended leading edges, surfaces that generate controlled vortices at low speeds, increasing lift without the need to physically extend the wing. Instead of moving the entire wing, the air itself was moved. Another key element was the use of advanced composite materials. Unlike traditional aluminum, composites allow for lighter, stiffer, and more fatigue-resistant structures. This made thinner wings possible, optimized for high speeds, without sacrificing structural strength or durability. At the same time, stealth systems changed priorities. Variable geometry wings introduced multiple problems in this regard. Joints, gaps, shafts, and changing surfaces that reflect radar signals unpredictably. From a stealth perspective, a fixed wing, with carefully calculated geometry and continuous surfaces, is vastly superior. Every angle can be optimized to deflect radar waves away from the emitter. A variable wing system would disrupt that balance in seconds. Furthermore, the internal mechanisms required to move the wings occupy critical volume within the fuselage. That space is vital in modern aircraft for internal fuel, sensors, weapons bays, and electronic systems. Giving up that volume for variable geometry wings was no longer acceptable. Efficiency also played a central role. Although variable geometry wings offered theoretical advantages, in practice the added weight negated many of those benefits. A well-designed fixed wing, combined with advanced electronic controls, proved to be more efficient in the overall mission balance. Although today they may seem like a relic of the Cold War, variable geometry wings, they continue to appear, quietly, in advanced engineering discussions. No, not as an immediate solution, but as an idea that could be reborn under new technological rules. The biggest problem with the movable wings of the past wasn't the idea itself, but the technological context in which they emerged. In the 1960s and 70s, control systems were analog, materials were heavy, and simulation capabilities were limited. Every solution had to be physical, visible, and robust. Today, that environment has changed radically. Current research programs are exploring what are known as adaptive wings or morphing wings. Unlike classic variable geometry wings, which rotated on an axis, these wings seek to subtly change their shape using smart materials, flexible structures, and nearly invisible internal actuators. In this approach, the wing doesn't move as it did on the F-14, but rather deforms in a controlled manner. The goal is to optimize aerodynamics in real time without introducing joints, gaps, or complex mechanisms that compromise stealth or reliability. Agencies like NASA and DARPA have funded experimental projects where wings modify their curvature, thickness, or profile during flight. In laboratory tests and unmanned prototypes, the results have been promising. Improvements in fuel efficiency, reduced drag, and better control at various speed regimes. However, transferring these technologies to operational fighter jets remains an enormous challenge. Military requirements are extreme. High G-forces, variable temperatures, impacts, vibrations, and absolute reliability. A system failure in a civilian aircraft might be a problem. In combat, it could be fatal. Furthermore, modern aircraft already accomplish their missions without the need for movable wings. The F-22, the F-35, and future sixth-generation fighters have demonstrated that the balance between speed, maneuverability, range, and stealth can be achieved with highly optimized fixed wings and advanced electronic systems. Another key factor is combat doctrine. Today, air superiority is not defined solely by close-range combat or top speed. Sensors, electronic warfare, long-range missiles, and networking have completely changed priorities. In this context, the marginal advantage that an adaptive wing might offer does not always justify its complexity. Even so, there is one area where variable geometry could find a new home: unmanned vehicles. Long-range strategic drones, hypersonic platforms, or experimental aircraft could benefit from adaptive wings without exposing human lives to mechanical risks. In unmanned vehicles, the design margins are different. Higher failure rates, shorter life cycles, or highly specialized configurations can be accepted. In that context, the idea of adapting the wing shape makes sense again. So why don't we see variable geometry wings on new fighter jets today? The ultimate answer is clear: because they are no longer the best solution to the current problem. Not because they are useless, nor because they have failed, but because they have been superseded by a more efficient combination of advanced aerodynamics, software, materials, and modern military doctrine. Variable geometry wings were a brilliant response to the limitations of their time. For decades, they represented the pinnacle of aeronautical ingenuity. But the history of aviation doesn't advance by adding complexity, but by replacing it with more elegant solutions. Today, instead of wings that move, we have airplanes that think. Systems that anticipate airflow, correct instabilities before the pilot perceives them, and optimize every second of flight without a single additional mechanical part. That doesn't mean the idea is dead. It means it's on pause, waiting for a context where it will make sense again. And if aviation history has taught us anything, it's that no good idea ever truly disappears. Variable geometry wings weren't a mistake. They were a necessary step, a bridge between classic aviation and the digital age of air combat. And now that you understand why some technologies disappear even though they work, subscribe to the channel and turn on notifications so you don't miss the next video. Because in aviation, as you have seen today, it is not always the most spectacular that survives, but the most efficient.